This is nanometers. This is voltage, and then this one here is frequency. But this is in nanometers, and it's increasing by 50. And it goes all the way up to 650. Yeah. And the voltage, I don't need it for the start, do I? No. But I'll put it in anyways. 0.940, 0.651, 0.398, 0.200, 0.060. Now the next here is the frequency, but that frequency is in 10 to the 14. So let me just do a little bit of a calculation. We have, C equals, F lambda. So then F equals C over lambda. C is 3 times 10 to the 8, and our lambdas are in nanometers, 10 to the minus 9, and I'll just call this X. So that is 3 over X times 8, 10 to the... Yeah, I don't know why it's 8. I guess because my brain was looking at the 8 here. 10 to the 17. So that is 3 over X times 10 to the 3, as you said, times 10 to the 14 hertz. So it looks like I do 3000 divided by X times 10 to the 14 hertz. That's the frequency. So 3000 divided by the first number. Come on. Alright. Equals 3000 divided by the first number. 7.5? Yeah. Okay. Next part is for 2 marks, so it should be only 2 minutes to do, and I'll do it now in a moment. You want to prove that result that they gave. Now, I know it looks complicated, but it's actually easier than you think. You have to think about the formulas I gave you for, what's it called, work function and photoelectric effect, which we did last week. So one of those formulas will be helpful there. I'll give you 1 minute, 1 or 2 minutes. We'll do it now. Sorry, the video was just paused there as I was explaining it. But what I'll do is I'll just put this on full screen, so if you're watching the video you can at least see my little proof here of that one. So the energy of the electron released from the battery must match the energy of the electron released by the metal plate, and they're both going in opposite directions, so you try to stop it. Anyway, try the next one for me please, the graph. So yes, Irva, you can put 10 to the 14 in the unit on the x-axis, and voltage is just in volts there. So insert chart. Okay. Right, so this is question 4, and the x-axis is frequency in 10 to the 14 hertz, and the y-axis is voltage in volts, and yeah, which I see some people had a graph that looks like this. Well, we need to put the straight line in. Like this. Let me just shrink it a tad. Come on, there we go. Just pop it up there in the corner. Right. Right, there you go. So you should have something that looks like that. Do you? Good. How many marks for that? 4 marks. Okay. Now, the next part. Use the graph to determine the value for Planck's constant. And you can use the value for E as given, that you know it. So, if you look back here, what do we need to use, the slope or the C? The slope, yeah. You have here that the slope, n, equals h over E. So therefore, E equals h over the slope. No, sorry, wrong way. I want h. So therefore, h equals the slope n multiply the E constant. So we need to get the slope n from our graph. So you can look at a big triangle here. I can see that this triangle is 1.4 units tall, and then it goes from 7.75 to 4.5 on the x-axis. So give me the slope, please. You can use mine or you can use yours. Well, considering a computer program made it, yes, mine will be better. Yeah, so the height divided by the base. Well, it looks like it's gone from 4.5 to 7.75. No, I want the slope. The height over the base. Okay. What did you get for the slope here? 0.431. Okay. Let's see how accurate that was. Come on. Insert equation. Very good. It's 0.4209. So if you've got 0.421, that's great. So the answer here would be 0.421. Now you have to be really careful though, because don't forget we have units in the x-axis 10 to the 14, isn't it? Mm-hmm. So it's actually 0.421 over 10 to the 14.
But do we need to include it if we... Why is it over?
No, hang on, we're getting a bit confused here. What's the formula for slope? No, look at me. Joshua, look at me. It's the y over the x. So the y, what was your height for y? 1.4. And what was your length? Yeah, but it's actually not 3.25, but rather 3.25 times 10 to the 14.
Sorry, what was the 1.4, right? There you go.
My goodness, it's going to be one of those days, isn't it? That will help some. Well, do you want the answer about how I got the height? Sure. So, step 1, open your eyes. Step 2, look at the graph. Step 3, look at the height. 1.4.
Well, that's not the last point.
Oh, I know it's not. But you take the biggest triangle you can draw on the graph for most accuracy. I am drawing a super big triangle that starts here and goes all the way up to the top.
So you mean to start from 0?
I started from the ground level and went all the way up to 1.4. So the height of the triangle is and the base is 7.75 minus 4.5, but it's 10 to the 14. The base is a lot bigger than it looks on the graph because of the unit. So that's why I have 10 to the 14 down below here.
So the slope is 10 to minus 15.
Yeah, which is good because h should be a really small number, so it helps to make it small. And what is the value for e? It's 1.6 times 10 to the minus 19?
Yeah.
1.6 times 10 to the minus 19. So this would be 0.421 times 1.6 times 10 to the minus 33. Yes.
What if one exam I forget it into 10 to 12 for you?
Well, then you lose marks. Because, you know, it's like wrong and stuff. What number do you get here? I'm really hoping a number like 6 point something.
0.674.
Yep.
0.
I know, but I'm going to move one of the powers.
Okay, then it's 6.74. Then it's minus 32. Minus 34.
Yeah. Now look, how does this compare to the true value of Planck's constant?
Perfectly accurate.
No, not at me.
Yeah. So, doesn't it?
Yeah. Now think about this. Remember we did 2 experiments to calculate the mass and the charge of an electron. Do you remember that? There was the one where it's traveling in a path, and then I can't remember what the other one was. But we got the charge to mass ratio, and then we got the charge. Oh yeah, that was it. We used the oil drops experiment to get the charge, and then we used the one in the field when it travels in a circle to get the charge to mass ratio, so we know the charge and the mass. And now you can use this experiment to get the h. So what I'm trying to show you is, even though these numbers are extremely small, we can still do experiments to get them very accurately. So we now know the h, the e, and the mass of the e.
If we didn't draw the line to the highest point, we just use extra normal y2 and y1, would we still get an accurate time?
No, because the points was all lying perfectly on a straight line.
But I used that and I got 0.411.
Okay, it'll be close. I'm just saying, please just do what I ask you to do. And you should draw, the marking scheme says the student should draw a triangle that's approximately 3/4 the size of a graph paper. Okay? So draw a big triangle.
So if I take the size of 3/4, then
Sorry, I'm speaking English, am I? Yes?
Alright.
I am, right? Good. So the marking scheme says draw a triangle that's at least 3/4 the graph paper. So your question is, what a triangle that's 3/4 the size do? What do you think the answer is? Yes. And do you think I'm going to measure your triangle to make sure it is exactly 3/4 anyway? No. I've got enough to be doing with my time. Right. Oh dear. Question? Yeah.
Should we start on 0?
We should. It's just my program's not doing that. If I look here, I should really start at 0. It's just my program doesn't do that. Yeah, I don't know how I can force it to go to 0. But anyway, your part should start at 0. Alright, the next question here is use your graph to calculate the wavelength, the maximum wavelength. So if I go back to my formula here, oops. Now just remember, you have this result, that the maximum kinetic energy is equal to the work function. No, sorry, that's not what I want. No, I'm doing something more complicated. I just want the maximum wavelength. So, you want the energy equals HF. This is of the light, yeah? But you can use your C equals lambda F, so we can get energy equals HC over lambda. So if we want maximum lambda, that means we want minimum energy of the light. So then the question is, they want the minimum energy of the light. That means they want the smallest energy that will release the electron so that it has no kinetic energy. So do you remember this situation, no kinetic energy? So that means we have 0 equals, kinetic energy is 0, HF minus work function. Yeah? So in other words, you have HF equals work function. So F equals work function over H. So then lambda, which equals C over F, would equal CH over work function. Now do we know H? We do. Do we know C?
Yes.
We do. Do we know work function? No, but we could know it.
Didn't they?
No, they didn't. But we can get it from this formula here, that this is equal to the C on the graph where it crosses the y-axis, the intercept. So minus work function over E equals minus. So can you tell me from your graph where does it cross the y-axis?
We can't see now.
Oh, you can't? Hang on, let's see. Does anybody's graph?
Oh, so 1.9. Minus 1.8.
Oh, sorry, I can see it here, can't I?
So
It's minus 1.889.
So on the exam we have to draw, like if we see that in the positive part, the graph that covers the y-axis, we should.
Oh yeah, you always want to draw your graph so it crosses the y-axis, given enough space. So the work function is 1.889 times E. So I can put that in there and I get wavelength equals CH over 1.889 E. So if you type this in on your calculator, what do we get? We know the C, we know the H, we know the E, and we have 1.889. Now I'm guessing that the answer would be something like about, I don't know, 750 nanometers.
Do we need to use the H that we get?
I would accept both in the exam.
What year were
There's only one E, the electron. So, 6 point what? So 657 nanometers.
No. Minus 7.
Yeah, but you said 6.57. I'm saying 657 nanometers. No, it's an awesome question. What's wrong? 6.62. Look, you're not listening. Someone just asked me that question 100 seconds ago. Now, there is another way to know if your answer is roughly right. If you look at your table here, so I need to delete my graph. Go away, graph. Delete. Delete.
Just go to the new.
No, but I want the numbers there I had. There we go. Now, what's happening as the wavelength increases? What's happening to the voltage? It decreases. So it doesn't make any sense here to have negative voltage, because then that means instead of stopping the electron, you're, I don't know, helping it or something. It doesn't make sense.
No, you're moving it.
You're the one causing it to move, yeah. So anyway, really the smallest voltage here is 0. So that means the biggest wavelength should correspond to a voltage of 0 as well. Now look at what's happening to the wavelength. It's getting bigger and the voltage is getting smaller. So we have 0.06 as the last reading. This makes me think that the answer should be more than 650, but not much more than 650. And the answer is 657. Of course, you'd be worried if the answer was less than this. But anyway, that's not important. I'm just saying, before you did the calculation, I had a look at this table to get a feeling for what type of answer you should get. So you're looking at an answer a bit more than 650. Okay.
That's changed in the next part there for the work function. So probably they're expecting us to find the wavelength below the work function.
Oh, so my guesstimate is what they wanted you to use, but more accurately, was it? Let me bring the table back. Undo. There we go. Yeah, so I think, hey guys, please note, this is an example where I said, no, look at me please, it'll make me feel better, thank you. Remember, sometimes I said it's easier to do the next part first. Sometimes. I feel this is one of those questions. But there must be some way to do this one without getting the work function like we just did. And I think what it was is using the graph. I think what they imagine students doing here is what I just said. Put the voltage at 0, see where this crosses the axis, take that frequency and convert it into a wavelength. So if you do C divided by 4.5 times 10 to the 14. Please tell me what you get. Please type it in.
Wait, it needs to cross the y-axis, not x-axis.
No, we want the voltage to be 0, so we're finding the root where it crosses the x-axis. 6 and 7.
6.67.
Yeah, 6 and 7. And what did we get when we did it the other way? 657. 657? Yeah. Okay, so just closer. And anyway, this is not as accurate because I must read it from the graph.
But in this question, they say use the graph.
Oh yeah, but I did use the graph because I got my work function. Because I can only get the work function from the graph. I understand. I think the way we just did is quicker, but no matter, we now have the next part finished. What's the next part? Work function. And what did we get for the work function? It was 1.889 wasn't it?
And we need to clean the electron volt. So it's just 1.8.
Oh, no, right. They wanted an electron volt. Yeah. So the answer is 1.88 electron volts. Alright, so that's cool. So what's next now? The maximum kinetic energy is... When lambda is 400 nanometers. What is this maximum? Maximum kinetic energy is when half mv squared equals the work function. Is it? No.
No, this is the minimum.
Hang on, I'll write it down. I can't do it in my head. So just before we go on, the work function was 1.889 electron volts, yeah? Okay. Next part is the maximum kinetic energy. Oh, when the wavelength is 400, sorry. So I see that there.
Doesn't mean just use HF minus work function.
Yeah, maximum kinetic energy, I think the word maximum there is a bit confusing. They could have said, what is the kinetic energy at 400 nanometers? No. You see, this is why people ask me the same question 1 minute later. So listen. They could have said, what is the kinetic energy when the wavelength is 400 nanometers, assuming no energy loss. Another way to write that sentence is, what is the maximum kinetic energy? In other words, if no energy was taken away from the kinetic energy. This is different to the question, what is the minimum possible kinetic energy and what is the maximum possible kinetic energy? They are different questions to what is the maximum kinetic energy when the wavelength is 400 nanometers. That is the same as asking what is the kinetic energy when the wavelength is 400 nanometers. So as Paul and other people were saying, we just use the regular formula. The kinetic energy after the electron is released is equal to the energy before the electron is released. We know H, we can know F, we know this one, and this is what we want. So it's hc over lambda minus 1.889 E. hc over 400 times 10 to the minus 9 minus 1.889 E. And we know H, and we know C, and we know E. So please tell me on your calculator what you get here.
1.9 times 10 to minus 19. Can you put that small?
Oh yeah, because it's only an electron, so it shouldn't have much kinetic energy. I think this is a great question in the exam. I think it is quite an easy question, really. It's quite easy. The last part is easy as well. What is the de Broglie croissant pastry breakfast wavelength of these electrons? So we have wavelength equals h over p, which equals h over mv. The only problem is we don't know the v, but we know the kinetic energy, so we can get the v from that. The formula for kinetic energy is a half mv squared. So this would be h over m, and the v would be 2. Well, let me try. Yeah, I'm trying to. Yeah.
Square root of 2 kinetic energies over m.
Yeah, multiply this by 2, and then divide it by the mass of an electron, and then square root it. So it'd be square root 2 times 1.9 times 10 to the minus 19 over the mass of an electron. Now I don't have a calculator, so I want to clean this up a little bit first. You can do it for me. You're going to help the teacher out here. This is the same thing as h over root the mass of an electron root 3.8 times 10 to the minus 19. This is the same as h over root the mass of an electron. If I divide this by 10, root 38, 10 to the minus 10.
Where did your mass go?
Which mass?
The one
I cancelled it with this one to make a root n. So this is h times 10 to the 10 all over root 38 times root the mass of an electron. Now you don't need to do all that. I don't have a calculator, so I'm trying to simplify as much as possible. What is the h?
6.6
Times 10 to the minus?
34.
So this is minus 24 now. And what's the mass of an electron?
9.109 times 10 to minus 31. Memory just
What's wrong?
just a look at me and try to find ways to get the number.
Is there a problem? I'm trying to do this without my calculator because, I don't know.
109.
What's the Planck constant in the list of constants?
Why is Planck constant what?
In the list of constants.
I can't hear her.
In the list of functions. Because they say use the value of h given in the list of
Yeah, use h, not the h from your graph.
functions.
That's what they're saying.
The list is equal to 2.
Oh, yeah, give me the real h, please. Want the real time constant, please, stand up. What is it?
6.6.
Okay. Can,
You gave it.
yeah, no, that's okay. I just want to see what it says in the exam book. 6.63 is what's in the formula book here. If you do it to 2 decimal places. Okay. Oh, please. 6.63 over root 38 times 10 to the minus 24, root 9.101, and then this would be something, 10 to the minus 31 over 2. So I don't know, this is about 3, and this is about 6, and this is about 18, this is about 0.33, so it's going to be something like 3.3. This is minus 15.5, 10 to the 3.3 nanometers.
No. 1.13 nanometers.
Well, at least I got the nano part right. What is it?
1.13
1.13 nanometers, alright.
Not bad.
You know what? For no calculator, it's not that bad. It just says 1.3 and I said it's 3.3 nanometers. So I have the correct order of magnitude. I didn't say it was millimeters. Yeah. And that means, so you see, that's 20 marks.
Horrible question.
Who liked this question?
The only problem that we had now is we didn't have a graph name.
That's the only problem. Yeah. How many people do you think did this question last year? Because this was last year's question.
No, yeah.
0. I don't know why. Nobody did it.
I didn't.
How many people did this last year, do you think?
No,
0 people did it last year.
You just said it, yeah.
Yeah. I don't know why though. My advice in the exam is you always do the graph question. Hey, what do you always do in the exam?
The graph question. With your English question.
And the material.
B1, B2, B3.
Oh yeah, material is great, but you don't get it all the time. But you always get a graph question.
So B1 to B3, yeah, much easier.
I don't know what you're talking about.